These two machines are sharing the exact same platform, yet they are separated by 2 centuries of engineering. On the left, an iron boiler from the early days of steam. On the right, a sleek, aerospace-grade bullet train. The performance gap between them is vast. The steam engine reached its limit at roughly 15 miles an hour, while its modern counterpart cruises effortlessly at over 200. You might assume reaching those speeds was a simple matter of scale, building larger boilers and more powerful engines to push the old designs faster. But scaling up hit a wall. Reaching 200 miles an hour required engineers to solve a complex series of problems regarding weight, friction, and air resistance. To cross that threshold, engineers had to move beyond the heavy mechanics of the 19th century and apply aerodynamic principles used in modern aviation. In the early 19th century, steam power enabled mass transit on a scale previously unimaginable. But the technology was restricted by the materials and physics of the time. A locomotive generates power through heat and pressure. You burn coal in a firebox to boil water, creating steam that is piped into cylinders to push heavy iron pistons. This design creates a weight-to-power bottleneck. To generate more speed, you need higher steam pressure, which requires a larger, thicker boiler and more coal, both of which add massive amounts of weight to the vehicle. That extra weight increases friction on the tracks. Eventually, the engine becomes so heavy that the added power is entirely consumed just to move its own mass forward. Steam had hit a physical ceiling. To go faster, trains had to become lighter, which meant removing the heavy fuel and the boiler from the train itself. Electrification solved the weight problem. By drawing power from overhead wires, the train no longer had to carry its own power plant, allowing it to be much lighter and more agile. But as speeds crossed 100 miles an hour, a new invisible enemy appeared: atmospheric drag. At high velocities, the air begins to act like a solid barrier, pushing back against the front of the train. For blunt-nosed trains, this created tunnel boom. As a train entered a tunnel, it pushed a massive wave of compressed air ahead of it, which would exit the other side as a loud, structural damaging shockwave. Engineers found a solution by looking at the kingfisher, a bird that can dive into water with almost no splash. The kingfisher's beak is a perfect wedge. It's designed to slice through a denser medium, water, without creating a pressure wave. By copying this specific geometry, designers created the long, sloping nose of the modern bullet train. This allows the vehicle to slice through the air, eliminating the tunnel boom and reducing drag. Reaching 200 miles an hour meant train engineering had to move away from traditional rail mechanics and into the world of high-speed fluid dynamics. Even with perfect aerodynamics, there was one final hurdle. If you placed this high-speed train on 19th century tracks, the results would be catastrophic. Traditional tracks consist of segmented rails laid on loose gravel. At 200 miles an hour, the extreme vibration and kinetic energy cause rails to buckle and gravel to shift, leading to derailment. Modern high-speed lines use continuous welded rails with no gaps, anchored to massive concrete slabs. This creates a rigid, unchanging surface that can handle extreme forces. Curves also have to be heavily banked. This tilt uses physics to redirect the outward centrifugal force downward into the track, keeping the train stable through turns. High-speed rail isn't just about the vehicle. It's an entire system designed to safely manage and cradle massive amounts of kinetic energy. Looking at these two together, we see the results of 2 centuries of progress. One was built to conquer mud and distance. The other was built to glide through the atmosphere. The achievement isn't simply the top speed, but the fact that it is done with absolute safety and daily reliability. This evolution has changed the way we view our landscape. Cross-country journeys that once took days of difficult travel are now reduced to smooth 2-hour commutes. The legacy of the railway's evolution isn't just about moving people faster. It is about how these connections have bridged the gap between isolated cities, creating a more integrated and accessible world.